Charles here, and welcome to the Undercurrent Stories podcast. Today on the show, I'm delighted to welcome Jamie Woodward. Jamie is Professor of Physical Geography at the University of Manchester, an author and a leading authority on rivers and microplastic pollution. Today, Jamie is going to take us on a history of the Earth, from the long ago beginnings of our planet to today. And we're attempting to do this in 45 minutes. So, if you're curious about our planet's origins, from space dust to a planet teeming with life, this episode is for you. I hope you enjoy the conversation. Hello, Jamie, and welcome to Undercurrent Stories.
Good morning, Bob. Delighted to be here.
Fantastic on this wet and rainy day in England.
Yeah, a bit soggy up here in Manchester too.
It is, isn't it? So I've just read your book, A Little History of the Earth. We were having a brief conversation before we went on air. Fantastic book. We'll talk about it in a bit more detail. And it covers sort of the Earth's history, I remember rightly, 4.54 billion years ago. And we've got 45 minutes. Do you think we can do that?
Yeah, well, I did it in 40 chapters. I'm sure we can do it in 45 minutes.
So, Jamie, just a little bit about yourself first, please, if that's okay. Could you just tell us a little bit about your background, your life growing up, and how you became interested in physical geography?
Well, I think when I was at high school, doing O-level, as it was in those days, O-level geography, A-level geography, field trips to the Lake District with the Outdoor Pursuits Club at my school in Warrington, and field trips to Snowdonia. I just got interested in landscapes, and I got interested in landscape history and how these landscapes change over time, with a particular interest. I'm a geomorphologist, and geomorphology is the interest in sort of Earth surface processes, how landforms develop, how they change over time. But my main interest is a particular focus on river systems and how river systems change over time. And that got me into a sort of a deeper interest into Earth history.
And how did you decide to write a book? What were the motivations for writing a book about the history of the Earth?
Well, a good friend of mine, Nigel Warburton, wrote A Little History of Philosophy, and that's been an incredibly successful book. And I liked the format of the little histories, and we can say a little bit about the history of that if you like. But I've written books about the Ice Age. I've edited books about the Mediterranean region, where I've done a lot of field research. But I thought I wanted to do something a bit more ambitious, and I thought, well, there's nothing more ambitious, if you like, than let's try the whole of Earth history and see if we can write that in a little history format.
And you talk about deep time, and that was a new concept to me, and it makes sense, obviously. But there was a particular part of it which I've recounted to various people, and I wonder if you just go through it, where you start off at the shoulder and go down to the fingernails in terms of describing time.
Yeah, the number of people have used that analogy. It was one of the favourite analogies of Stephen Jay Gould, the famous Harvard sort of evolutionary biologist. And so you hold the arm out, and the number of ways of sort of illustrating the great depth of the time depth of Earth history. So if I stick my arm out here, so on my shoulder is the origin of the Earth, the formation of the planet 4.5 billion years ago, and then slowly moving down the arm through time, round about here on the muscle here, you've got sort of maybe 3 billion years ago, you get the origins of the first life. We've got oceans at that time, and then changes in the atmosphere, and then we can run right through to the palm of my hand into the sort of Mesozoic era, when we get the evolution of the dinosaurs, and then right down to the fingertip, to the tip of the nail on the middle finger, is the evolution of humans, and then human history. And I think I mentioned that a single nail file could just scrape away the whole of human recorded history. So that analogy is very useful to illustrate the great time depth of the planet, but also the brevity of human presence on that planet. Because, of course, I talk about how, of course, the biblical narrative about a young Earth, the origin of Earth from the book of Genesis, and that the Earth was created for humanity. That was a huge shock in the end of the 18th century and going into the 19th century, when the first geologists started to recognise that Earth history had a much deeper history than that was recognised in the Bible, and that had important sort of philosophical context for humans and our history and our place in this universe.
That's a great. I just love that analogy. It's so easy to almost remember. And
and there are lots of others as well. Like, you have a great big thick book, and then the humans appear in the last paragraph on the last page, or a clock face, and it's the last couple of seconds to midnight. So either way, it illustrates that for a long, long time there were billions of years of Earth history without any humanity at all, and we have a very, very deep history.
One thing I would like to say is that after reading the book, you sort of, the various things that I learned and explored and all the rest of it, and will do in future. But one of the things that came out from it was how interconnected and balanced the Earth is in terms of all its systems. And I found that absolutely fascinating. How the moon makes it just right where the moon is, magnetism, and we could go through. I'd like to talk about some of those subjects, but that to me was absolutely fascinating.
Yeah, I pull a lot of those strands together in one of the later chapters when I talk about planetary boundaries, but there is a whole set of factors that work together to make our planet habitable. And I talk about the Earth as a system. So there's the great spheres of the Earth system. There's the lithosphere, which is the rocks, the crust, the mantle, and the hard stuff. The atmosphere, the gases around the planet. The biosphere, which is all life and living things. The hydrosphere, the water. And then the cryosphere, which is all frozen water. So those great spheres of Earth history, which have evolved over time and have interacted in different ways over time, but have combined in different ways to create a habitable planet. So one of the remarkable features of this story is that, the planet started out as space dust, rocks and dust traveling through space that accreted together to provide a sort of a rocky planet. And then eventually that evolved and conditions were favorable to create the remarkably diverse, biologically diverse planet that we have today, with all the wonderful plants and animals and ecosystems, etc. So from very sort of inhospitable beginnings, and pretty early on, actually, those habitable conditions emerged. And then I tried to list them, and there are others. The magnetic field protects the planet from dangerous radiation. We're just the right distance from the sun, so it's not too hot, not too cold. What sort of we often call the Goldilocks zone. And then all the other factors, the presence of water, et cetera, which meant that it created conditions that were favorable. And that may be certainly unique in our solar system, but maybe unique in the universe. We don't know. But it means that Earth is a very special place. But it also means that habitability is not guaranteed.
You mentioned there the Goldilocks zone. Could you elaborate on that, or is that everything you've just said?
No, one of the chapters, I think in chapter 3, I talk about the Goldilocks zone, and I do that through talking about, there's a very famous photograph that was taken, I think in 1972, called the Blue Marble, became known as the Blue Marble photograph, which was taken by one of the Apollo missions. And it was the first time that humans had actually seen the whole of the Earth from space. There's the famous Earthrise photograph that was slightly earlier, but the Blue Marble photograph was just snapped as a moment in time. The whole of the Earth was illuminated by the sun, and the astronauts were just the right distance away from the planet to capture it. And it shows the Earth. You can see the oceans. You can see the sort of the plants on the land surface. You can see the clouds in the atmosphere, and it basically shows that there's this blue planet, this special place, surrounded by the infinite darkness of space. And that Blue Marble photograph, and I elaborate on that by saying that it's a watery planet, it's a blue planet, and it is that because it's just the right distance away from the sun. So if it was closer to the sun, the water would evaporate. If it was further away, it would be colder. That water would be frozen. So we're in what is known as the habitable zone. So it often called the Goldilocks zone. It's not too hot, it's not too cold. Conditions are just right. And with the atmosphere, that creates a sort of temperature on Earth where water can exist as a solid, as a liquid, and a gas, and where liquid water can be abundant on the surface. And that's certainly unique in our solar system, which creates this sort of watery world that eventually became conducive to life. So yeah, the Blue Marble photograph also was really interesting because it's become an icon of the sort of environmental movement as well, that illustrates the fragility of the Earth system. Yeah. So I thought that was a good vehicle to sort of to explain some of those ideas.
Yeah, we talk about the Earth being 4.54 billion years old. For any listeners that want to ask this question, how do we know that?
Well, I have a chapter about how old is the Earth, and there's a long history about people speculating about the age of the Earth system, from Ussher's biblical chronology to ideas in the 19th century from Kelvin and others, and until the mid 20th century, until we had scientific dating using radioactive isotopes, it wasn't possible to come up with a precise age for the age of the planet. But in the just after the Second World War, there was a famous paper published in Science, which had been dating meteorites, because meteorites are basically the same age as the Earth, or maybe just in some cases just a little bit older. And it was possible using lead isotope dating, to use those isotopes to calculate the age of the planet. And the ages that came up then were roughly 4.5 billion years. And the numbers, actually, that scientific work was really pretty precise at the time. And the numbers haven't actually changed that much in the intervening period. So ballpark figure, the Earth is about 4.5 billion years old. But that's based on what we called sort of geological clocks, if you like. Radiometric decay has allowed us to date those very, very ancient rocks.
But to do that, we have to look at meteorites outside of Earth to get Earth's
Yeah, because I have a chapter also on the oldest rocks, and so there are some very old rocks on the Earth that relate to some of the earliest crust. But the original old rocks of the first crust, of course, are long gone. They've been eroded away because of plate tectonics and because of erosion, because the Earth is so old. But the moon is a little bit younger than the Earth, so we can date moon rocks, but we can also date meteorites that have landed on Earth since then, because they're about the same age as our solar system. So dating meteorites gives us a good indication of the age of the planet.
What's the difference between asteroids, meteorites, and meteors?
Oh, right. Okay. Now you're asking. I've got to think about this. Well, asteroids it's a size thing. First of all, asteroids are huge. Asteroids. It was an asteroid that hit planet Earth that was responsible for the extinction of the dinosaurs. Or certainly made a huge contribution to that. Meteors are effectively shooting stars. You see them glowing in the night sky as they're sort of burning up, coming through the atmosphere. But they only become a meteorite when they land on the Earth's surface. So meteorite hunters going to places like Antarctica, for example, they can see meteorites sitting there on the snow and the ice. I think it's a meteorite once it's landed on the surface.
It's interesting, Jamie, how you mention various people in the book and the significance that they've had on the understanding of the development of the Earth. And one of the people that came up was James Hutton. Could you just tell us a bit about James Hutton?
Yeah, James Hutton had a remarkable influence on the early development of geology. And he was based in Edinburgh and did some of the really important work in the sort of latter part of the 18th century. But he was part of a remarkably influential group of thinkers as part of the Scottish Enlightenment, if you like, which included the philosopher David Hume, Adam Smith, the economist, John Playfair, who was a professor of natural history at Edinburgh University, and also Robbie Burns, the poet. And they were known as the Oyster Club, and they used to meet around Edinburgh and have dinners in various places and sort of chat about natural history and philosophy. But James Hutton was a farmer, and he was a great observer of the landscape, and he was made huge contributions. Principally, he had ideas about the rock cycle, that the Earth was continuously cycled in terms of the creation of mountains and the erosion of mountains, the creation of sedimentary rocks, and the process being very continuous. He also put forward ideas that geological processes operated over very long spans of time, and they operated relatively slowly. He didn't have much time for catastrophic events, and which led to the idea of uniformitarianism later in the 19th century. So James Hutton came up with the idea that the Earth was very, very old indeed. He looked at the rock record, he observed various sections, and recognised that the Earth must. He couldn't put a number on it at the time, but he recognised that Earth must be very ancient indeed, and that geological processes needed extended periods of time to create the geological record and the sediments that we could see.
So that was pretty significant, really, wasn't it?
really important at the time when geologists were recognizing that we were dealing with a very ancient Earth that must be far older than the biblical chronology. An Earth system of just 4,500 years. He recognised the Earth system must be much older indeed. So he set the scene really for the development of modern geological science in the 19th century and beyond.
And one of the other characters that comes up in the book is the lady heavily involved with fossils, and the amount of energy and effort that she put into finding them.
Mary Anning. Mary Anning came a little bit later, and I devote a whole chapter to Mary Anning because her contributions were extraordinary, and she's often portrayed as a woman who kind of walked along the coast collecting fossils, collecting bones, and putting them in a basket. But she was much more than that. She understood in many ways how these ancient creatures lived, and she was a fantastic excavator and preserver of fossils. She really understood these creatures and the ecosystems that they lived in. So it's often reported, that people stole her ideas, and her fossils were reported in papers presented in London. But actually, she was widely respected, highly respected in geological circles. And when she fell on hard times financially, members of the Geological Society persuaded Robert Peel to grant her a pension. So Mary Anning was a remarkably influential figure in paleontology in the first half of the 19th century.
Yeah.
And she was describing all these weird and wonderful marine reptiles that were living in the Jurassic and the Cretaceous oceans at the time when dinosaurs were dominating the landscape.
You mentioned in the book how over periods of time the Earth was very, very hot or very, very cold. In fact, you devoted a whole chapter Snowball Earth. Yes,
well, that's a fascinating period of Earth history, which is a geological time known as the Cryogenian, and this was round about the time when the sort of the first complex life was emerging in the oceans. But Snowball Earth is a fascinating period because some of the hardcore Snowball Earthers would argue that the planet was completely frozen. The oceans were covered in sea ice, often maybe to a depth even of a kilometre. And the landscape was covered in ice sheets. And so from space, the Earth would look like a great big ball of ice. Some have argued that climatic conditions weren't quite so extreme, that not everywhere was covered in ice. But I think everybody agrees that this was the coldest and the severest and most prolonged ice age in Earth history. And, these ice ages lasted much, much longer than the ones of the more recent Pleistocene ice age, for example. But also what's remarkable is that we had, ice sheets in the tropics. Today we have small glaciers in very, very high mountains in the equatorial regions. But glaciers down to sea level, that we only have those in the polar regions. But during Snowball Earth, there were glaciers went down to sea level in the tropics. So that was a remarkable climatic deterioration.
I guess as a physical geographer, you must spend a lot of time going to some of the places around the world where you can actually see these things that you talk about.
Well, yeah, I've done fieldwork more of my fieldwork over the years has been in the Mediterranean region. I'm talking about glaciation there. So I've done work on glaciation in the mountains of Greece, in the Pindus Mountains. So it's not widely recognised that during the last ice age, many of the mountains in the Mediterranean, in Spain, in Italy, in Greece and Turkey, had pretty big glaciers, several kilometres long and small ice caps. And in some parts of the Mediterranean today, in Turkey and parts of Italy, we still have glaciers today. But you think about Mediterranean holidays and lying on a beach somewhere in lovely, warm, bright sunshine. During the Ice Age, there were pretty big glaciers in many of the high mountains across the Mediterranean. And I've done quite a lot of work on those glaciers, but also on the impact that they had on river systems downstream, and what impact they had on early humans at the end of the Ice Age, who were sort of subsisting and hunting ibex and chamois in those regions.
Sounds very interesting.
I think so. And the other place I've worked is the Nile Valley. That's working with archaeologists at the British Museum. Spent sort of a decade and a half in northern Sudan, doing various field seasons, looking at ancient channels of the River Nile and how they related to early Nile Valley civilizations. And again, that was an area where we were using scientific dating to date these channels and to work out when they were flowing and how they related to the archaeology. So one of the strands that runs through my research is an interest in river systems and how they function as the Earth system changes and how humans have interacted with those rivers.
Another fascinating thing I learned or probably realised in a bit more depth was, I mean, I knew it as continental drift, but the amount of changes we've had with plate tectonics of where everything is in the world over time.
Yeah, I talked about Alfred Wegener's idea of continental drift when he put forward just before the First World War. But and he put forward the idea of a supercontinent, Pangaea, and that all the land masses were once collected together with this supercontinent, and then over time it fragmented, it broke up, and those continents drifted, to where they are today. But what we now know, of course, is that Earth has gone through multiple what we call supercontinent cycles. And 200 million years in the future, the way that the continents are moving now, there's likely to be another supercontinent further down the track. But in the past, there have been previous supercontinents as well that have broken up. But of course, as they get older, it's very difficult to kind of be confident about the geography of those and to reconstruct those. There was a supercontinent called Rodinia, for example, in the Cryogenian period, when we had snowball Earth, when the Earth most of the Earth was frozen under very severe ice age conditions. So yeah, the geography of the planet has changed dramatically over time as the continents have drifted and ocean basins have changed in size, and that influences the ocean currents, it influences the climate. So what we call these boundary conditions, the fundamental state of the planet in terms of where the continents are and where the ocean basins are is a really important influence on climate, for example. And yeah, change is constant.
Yeah. No, it certainly hammers home in the book. And the other surprising thing that I found, and we talk about water. You look at all the water on the surface of the Earth, but there's actually more water inside the Earth.
I know that's a remarkable discovery. Yeah, and it's quite hard to think about actually. But when I was at school, we did the water cycle in geography. We'd have the evaporation from the oceans, and it forms the clouds, and then it rains on the land surface, and then it creates lakes and rivers, and the water then flows and returns back to the ocean. So we talk about the water cycle, and then when you get to university, they call it the hydrological cycle. Well, that's very much focused on the surface, on the sort of interactions between the atmosphere and the land surface and the oceans. But what we have a much better appreciation of now is that we mentioned plate tectonics earlier, that a lot of water is lost into the mantle at subduction zones, for example. So when you've got rocks that are saturated with water, when they go down into the mantle at a subduction zone, that water goes back into the mantle. And there's lots of water in various forms under pressure, not the water that we recognize at the surface, but certainly the water that's sweated out through volcanoes, for example. So it may well be that during Earth history, most of the water on the planet has been recycled through the mantle, maybe one or at least a couple of times. And the mantle is so huge, it may well be that there's at least as much water in the mantle in various forms as we actually have at the surface, and there may be more than that. There are different views on the amount of that. But what is clear is that when we do talk about the water cycle now, if we think about much longer timescales, we have to include the mantle as well, not just what's happening at the surface. And that's a fascinating idea.
Do you think we'll ever get down to the centre of the Earth?
No, there's lots of interesting films and obviously science fiction novels about that, but I think we have other priorities. But the Russians have tried to. They had a long-term drilling project which tried for decades to drill down to the crust mantle boundary, and that was unsuccessful. So no, I think that's pie in the sky.
What methods are there to determine different ages of the Earth? When I say ages, I mean different periods of the Earth. So pinpointing, because it's quite specific in terms of, this ice age was then, and then we had another one then. What sort of methods are used these days?
Well, a lot of my own research is focused on the Quaternary period, which is the most recent period in Earth history, which is about the last 2.5 million years. And I think one of the features of, since the Second World War, really, has been the huge advances in scientific dating methods. I mean, most people will have heard of radiocarbon dating, where you can date organic material, sort of fossil trees or seeds or even bones, for example. But radiocarbon dating only goes back about 50,000 years. So that's relatively, of course, recent Earth history. But there are other methods. I use methods like uranium series dating, which uses radioactive isotopes from uranium and thorium. Those dating methods can go back sort of 350, maybe up to 500,000 years under good conditions. And then there are new methods that are becoming into use, much popular now, called cosmogenic dating, which use cosmogenic isotopes, but isotopes from space, basically, that strike rocks at the surface and they build up an isotopic signal. And so you can measure how long a rock has been exposed at the Earth's surface. So cosmogenic dating is allowing us to date new materials, for example, and date new landscapes like glaciated landscapes or parts of Antarctica that have been scoured by ice. So there's a whole range of scientific methods. And I think that's one of the beauties of working in earth science, is that the various disciplines can share information, and you get information from physics and information from chemistry, and thinking laterally, you can think, well, actually, that could be a geological clock. That could help us to date these materials, whether it's organic materials or rock materials or whatever. But in very, very deep time, there are other isotopes that are used. So often isotopes of lead that allow us with very long half-lives, which allow us to date very ancient rocks. So we can date rocks back into the Hadean, for example, which is the first geological epoch.
Just asking for a friend, what is an isotope?
Well, so we have stable isotopes. So let's take in sense of radiocarbon. Carbon, for example, carbon has stable isotopes that don't decay, but carbon also has an isotope called carbon-14. Which is it's a form of the element that decays slowly over time.
Oh, okay.
And then that radioactive decay, we can actually measure that. We can actually measure the number of atoms that decay, and then we can calculate, for example, when you die, Bob, and when I die, we will start decaying, and we will start, radiocarbon it's decaying all the time, but it won't be replaced in our bodies. So over time, we'll be able to measure the amount of radiocarbon that has decayed from our carcass and calculate the age of when we died. That's sometime in the future. But there's a variety of methods that we can use that can to give us different timescales of dating, but also allow us to date different materials. And that's when we make the choices about which methods are most appropriate. But a lot of those dating methods are quite expensive.
Yeah.
Radiocarbon dating is about £500 a go, for example.
Wow.
So, and it's done in specialist laboratories. So we have to be careful with our budgets.
When you ask people about, if you say to somebody the history of the Earth, one of the prominent features of it are dinosaurs, because everybody remembers, everybody talks about them, and there's this thing, isn't there, about the dinosaurs were wiped out, they didn't last very long, but they were around for quite a long time, weren't they?
The dinosaurs first emerged in the Triassic period, and we hear mostly about the Jurassic, but so then the Jurassic and the Cretaceous, and the dinosaurs dominated terrestrial ecosystems for millions and millions of years, for the whole of the Mesozoic era, in fact. But in the book I talk about when I was about 6 or 7, my big brother Danny got a dinosaur book I think it was for his birthday. And we were looking through this book. This is in the sort of mid-70s, and we're looking through this book, and we're looking at the dinosaurs and learning their names. And they were portrayed as fairly dull, slow creatures, and they were sort of green, grey, scaly creatures. And I mentioned this is sort of dinosaurs for kids in the 1970s, and they talk about there wasn't really a satisfactory explanation for their extinction. They said they failed to adapt to a changing environment. It was all a bit vague. But what's remarkable over the last 30 years is that we've learned so much about the dinosaurs and how their appearance. Many dinosaurs were covered in brightly coloured feathers. They were really smart animals. They weren't stupid. They weren't dull. Some of them may well have been warm-blooded. Dinosaurs lived in the Antarctic during warm periods of the Cretaceous. So the amount of information we have now on the behaviour of dinosaurs and the landscapes that they lived in has been utterly transformed. So that book that I had in the 1970s sort of stimulated my interest in Earth history. But we know so much more about those creatures now.
In terms of the solar system, our solar system, 2 questions really on this one. You mentioned that there was once water on the moon. And there's also a discussion about we on Earth are the only planet that has plate tectonics. Could you just elaborate on that, please?
Well, 2 points there. Well, there's still water on the moon. I think there is water, but it's frozen. There is ice in the craters of the moon, and there is some evidence to suggest that there may be water or ice beneath the surface, just immediately beneath the surface of the moon. I think I talk about in the book about there used to be large volumes of water on Mars. We've done a lot of research now from the Mars rover and understanding the surface of Mars. There are lots of features, landscape features like deltas and river valleys and canyons and old lake basins, which show very clearly that there used to be a very active water cycle on Mars, just like there is on Earth at the present day. There's quite a lot of water on Mars at the moment, but it's frozen in the poles. There's a lot of water ice. What Mars doesn't have is an active hydrological cycle, i.e. water moving from liquid to solid to vapor and being cycled around the planet. It's stuck at the poles at the moment and it's frozen. What was the second question? Was it about plate tectonics?
Yeah, we're the only planet in the solar system that appear to have or have had plate tectonics.
Yeah, we're the only planet that has sort of planetary scale plate tectonics. There may be hints of, the moon, for example, and other planets have, active volcanic. Well, the moon has had volcanic activity in the past. There may still be some volcanic activity beneath the surface. But in terms of the crust or the outer shell of the planets being composed of a series of tectonic plates that are actively moving, as far as we know, Earth is the only planet that has a planetary scale plate tectonic system. And that's another interesting feature that makes the Earth unique. There may be plate tectonics on planets in other solar systems, but and then plate tectonics may have been present on Venus partly in the past, but at the present time, in terms of an active planetary scale feature, the Earth is the only planet. There aren't any other planets or moons in our solar system where we've seen that planetary scale activity.
If we talk about humans for a little while,
sure.
We've now got virtually 9 billion people on the planet. The book explains how interconnected everything is in terms of it. Can we sustain 9 billion people on this planet?
Well, I don't get onto this in the book, really. I mentioned, of course, that we're going to have 9 billion people before too long, but the book doesn't really offer any solutions to that. But just more generally, what I would say is that we need to take much better care of the living world in terms of preserving biodiversity, more sustainable forms of agriculture, reducing the amount of pollution, etc., etc. So if we are going to live in harmony with 9 billion people, we need to do that in a much more sustainable way than we are, because at the moment the numbers are pretty scary in terms of the way that we're heading.
Yeah, and you talk about the Anthropocene. This is the era that we're in at the moment, but it hasn't actually been formally ratified.
Yeah, there was a big hoo-ha in the earth science community. A lot of people got very animated and very excited about this, because there was a group called the Anthropocene Working Group who spent the best part of 15 years investigating whether we were in a new geological period and whether there would be some merit in defining a new geological period that was it was characterized by the dominant role of humans in the Earth system. And they put forward a proposal to a group called the International Stratigraphic Commission, or the International Commission on Stratigraphy, ICS, to formally define a new geological epoch, and it was turned down. So there was a lot of technicalities here around how you define a new geological epoch, because there's a group there, and I think I described them. They're the guardians of the geological timescale, and they make decisions about when does the Carboniferous begin, when does the Carboniferous end, etc. What dates should we recognise? And we have to recognise, is there a place on Earth in the rock sections where we can see this beginning of this period and we can see the end? Is it well dated? And so they had to fulfil various criteria for the Anthropocene. that had been used for the definition of other geological periods. Anyway, for a whole variety of reasons, their proposal was kicked out, and we are not living in the Anthropocene. It's informally. It's not a formal geological period or epoch now, but it's regarded as an event. So the Anthropocene term is still widely used, but a lot of geologists thought it was a missed opportunity to because defining the Anthropocene may well have focused the minds of policymakers. We're living in an era now where the planetary system, the planetary system is being dominated or influenced by human activity. In terms of global warming, in terms of influence on the water cycle, our influence on the biosphere. Humans were now a major player in the Earth system, and they thought that a new geological epoch would acknowledge that, and it may then focus minds and encourage people to develop better policies to manage that impact.
What would you like people to take away when they've read the book?
Well, I'd like people to enjoy the read of the book. I'd like people to obviously to find out new things about the Earth system. But I think most importantly, I wanted to make people more curious about the Earth system. I want people to think about, well, this is a gateway to a fascinating literature and fascinating stories. Whether you're interested in dinosaurs, whether you're interested in plate tectonics, whether you're interested in the whole sweep of Earth history, and to encourage people to go and find out more. So that might be going to university to do a degree in physical geography. It might be to do a degree in earth science, or just to want to read more and find out more about the Earth system. So I wanted to sort of, stimulate curiosity and get people to ask questions. But also in relation to your previous question, Bob, is maybe to get people to be better informed and to kind of understand why the Earth system changes. I spent a lot of time also talking about, the ingredients, the sort of set of ingredients that make the Earth system habitable, and I also talk about the big mass extinctions in Earth history, and also to make the point that habitability is not guaranteed. It's not a given. And there are other planets in the solar system, like Mars lost its atmosphere, Venus has undergone to super greenhouse conditions. These planetary scale conditions can change, and at the moment we're driving very, very rapid change in terms of warming of the planet, which has huge implications for the oceans. We're destroying the biodiversity in various parts of the world at a rapid rate. And talk about the Great Acceleration, how these things have really kicked in and accelerated in their rate since about 1950. But we do understand these processes, and we have strategies to deal with them. Homo sapiens, I make the point, means wise humans, and we're defined by sense and reasoning. So let's hope that we have the good sense to slow down some of these negative impacts and create a cleaner, brighter, better world. We have the capacities to do that, but of course the politics at the moment is pretty depressing.
I think we've done our 45 minutes. We've scratched the Earth's surface with this. And all I can say is there's a lot more we could talk about, but I would really urge people to consider buying the book. It's a fantastic book. What I liked about it from a practical point of view is that the chapters are quite short. So, most of us are pretty busy, very easy to pick up just before you go to bed or something. Wake up in the morning, just read a chapter, take you about 10 minutes. Absolutely fantastic. And the other thing was what I liked about it were the illustrations.
I'm delighted.
Which sort of sum up each chapter,
Yes, I'm delighted you've mentioned that, because Rachel Hibbs did the original artwork and those brilliant lino cuts. And I provided Rachel with some suggestions for the illustrations, and she produced that beautiful artwork, because I was quite keen that the beginning of each chapter has some beautiful artwork, but I wanted to make sure that artwork helped with the interpretation of that chapter. So one of the features of Little History books is that each book has a different artist that illustrates the books, and they're absolutely a key feature of the book that make them a beautiful thing to have, if I can say so.
Yes. Oh, it is. And what are you working on now, Jamie, in terms of books? Because this isn't the only book you have out. You got another few books as well, haven't you?
Yeah, I've done some very short introductions for OUP, for Oxford University Press, one on the Arctic recently, and then about 10 years ago, one on the Ice Age. And I'm taking a break from book writing at the moment. I'm maybe writing a book on microplastics, actually, but that's rather different story, rather more recent, because I've been doing research recently on river systems. Let's call them Anthropocene rivers, recent river systems, and sort of pollution and microplastics. So I've brought that theme right up to the present day. So maybe we could talk about that on another podcast sometime.
Well, we'd love to have you back. This has been an absolutely fascinating conversation, Jamie. Lots of things that perhaps some of us know a little bit about, but this goes into a bit more detail. My guest today has been Jamie Woodward. Jamie is author of the book A Little History of the Earth, and he's Professor of Physical Geography at the University of Manchester. You can find links to the book in the show notes. Thank you for coming on the show, Jamie.
Thank you, Bob. And if you buy the book, get it from your local bookshop. Delighted to be here. Thank you.